welcome back. This is lecture 26. So in the last lecture we were seeing how to increase the gain of our common source amplifier, and what was the bottleneck and what are the potential solutions, right? So we saw that if this is our classical common source amplifier, the gain that we were supposed to get, between this node V0 and Vi is Gm times RL, right? And in order to get larger gain, we have to use larger RL, right? So if we have to use larger RL, then we saw that it's not in our control to keep on increasing RL, right? Because if we keep on increasing RL, then what's going to happen? If the power supply is fixed and if I keep on increasing RL, then the voltage drop, the quiescent voltage at V0 will keep on going down, and after some value of RL, the drain voltage of the transistor will go below the overdrive voltage, and which essentially means that your transistor is gone out of linear. So what was the moot point? The moot point was, it seems like the gain is related to the quiescent drop across the RL, right? So if gain was related to quiescent drop across RL, which means that if I need larger gain, I would have to deal with larger quiescent drop across RL, which means that if I have a power supply, fixed power supply, which means then it will naturally mean that there is a maximum certain amount of gain that I can get from this configuration and not beyond that. Now the question is, what if I want to get more and more gain, higher and higher gain? What will be the limiting condition? The limiting case here is the fact that we have to search for a solution in which the gain is independent of the quiescent drop across the load. So essentially we were trying to figure out, can we replace this guy with something so that the incremental resistance or whatever that thing is independent of the quiescent drop across that thing, right? So, and we didn't look too further, because if we look at this transistor M1, right? If we look at this transistor M1, what is the incremental impedance looking into the drain? It's RDS, right? So we saw that incremental resistance of M1 looking into the drain is RDS, and this is independent of the quiescent drop across M1, right, i.e. PDS, right? So what is the key takeaway from here? The key takeaway, or I should not write independent of the quiescent drop, I should write so RDS independent. Yeah, right. So it is independent of the quiescent drop across M1 as long as the current is fixed, or even I don't have to write current is fixed, as long as M1 is in saturation, right? So as long as M1 is in saturation, what is RDS? RDS is 1 over lambda IDS, right? So what happens if I increase lambda? What happens if I increase IDS? If I increase IDS, then naturally it seems like the RDS is decreasing, right? However, we note that we have one more handle. What is the handle that we have? this lambda is proportional to 1 over L, right? So in other words, I can say that RDS is proportional to L by IDS. So if you increase L in order to keep RDS constant, sorry, if you increase IDS in order to keep RDS constant, I have a handle that I can increase the length, right? So in essence, this gives us we already see there is a solution, but the solution is looking into the drain of the of M1. However, we were trying to figure out if we can replace RL with another transistor whose drain will be located at V0, and note that the drain has to be for this new transistor, the drain has to be at a lower potential, right? So since because the current ultimately has to flow from top to bottom, since this guy has to be at lower potential, right? So drain has to be at lower potential, which means we cannot use an n-Mos transistor. So we went in search for another device, and as it turns out, a complementary device exists. It's called the p-MOSFET, right? And what were the characteristics of the p-MOSFET? The p-MOSFET characteristics were the current that flows from the higher potential to the lower potential, that is ISD, in saturation is equal to mu p times Cox times W over L, where mu p is the mobility of the carriers, which is hole in this case, times VSG minus mod of VTP whole squared times 1 plus lambda p VSD, right? Note that in these cases, in the cases of MOSFETs, p-MOSFETs that we will be dealing with, VTP is often negative. However, we will be using mod of VTP simply because we want the equations to look similar to that of a n-Mos transistor, and we don't want to learn a whole new bunch of equations, right? So that was a whole reason of this investing time in this. And what is a good thing about this p-Mos transistor? The higher potential is source, lower potential is drain, and if it is biased in saturation, the incremental impedance looking into the drain, right, will be RDSP, which can potentially be as high as the RDS of an n-Mos transistor. And as long as we can keep the p-Mos transistor in saturation, right, as long as we can keep the p-Mos transistor in saturation, then we can get high enough RDS, which is independent of the quiescent drop across the source to drain voltage, right? So, and then we said that we also implemented we also analyzed the incremental equivalent of this structure, and we said that, and we saw that the incremental equivalent for an n-MOSFET, right, for an n-MOSFET, the incremental equivalent was this. So this is source, gate, drain. This is GM times VGS, right? In case of a p-MOSFET, the incremental equivalent was exactly the same things, but flipped, right? So since the drain is in the actual picture, the drain is in the bottom, so we would like to have the drain connected at the bottom. The gate is wherever the gate was. The source comes out to be MOSFET. Okay, so this is the drain terminal, and you have a current source. This is the source. Okay, and we should also say that the voltages are taken between gate and the source, just like in case of an n-MOSFET. Okay, and what is this value of this current source? This has to be again Gm times VSG, right? If we because this equation has VSG, right? But if we say that we want an equivalence between the n-MOSFET incremental model and the p-MOSFET incremental model, we don't want to remember anything new, then we will say that we'll use Gm times VGS, right? And what will be the current direction? The current direction will be looking up, right? And then we'll be having this resistance here, which is again VDS, right? Okay, so these two are kind of these two incremental models are broadly the same things. We have again the gates terminal, source terminal, drain terminal. We have Gm VGS in both sides, right? And we also have the current flowing from drain to source, right? We also have the current flowing from drain to source. So in both cases, so essentially these two are incrementally identical, right? You have Gm VGS current flowing from drain to source in both cases, but the way we tend to sketch these incremental models is we flip it, right? We flip it because ultimately in the we know that ultimately in the actual model, right? In the actual model, in these guys, the drain is at a lower potential, right? So just because we want to have an equivalence, it is better to follow this flipped mode, right? Okay, so now where we stopped in the previous lecture was here, that what was the incremental model of this guy. The incremental model was the same old. So we have Vi here, Gm VGS, where VGS is equal to Vi. We have RDS and we have RL, which is incrementally connected to ground, right? The whole issue is, the whole song and dance that we are doing is because we wanted to replace this RL. Okay, so incrementally, what was the solution that we came up with? Incrementally, the solution was to replace RL with something which is the drain of the transistor, and we said that maybe the p-Mos equivalent is a good way to go. So what would have been the p-Mos equivalent in the incremental sense? So this so what we would do is we retain the n-Mos side RDSN, right? And this is Gm times Vi. This is gate, and here on the top side we would like to look into the drain of another transistor, which we know now has to be a p-Mos transistor. So what we will do, we'll replace the RL with the incremental equivalent of a p-Mos transistor. What is the incremental equivalent of a p-Mos transistor that we just did? Again, this is Gm VGS, for the PMOS, right? Then you have GDS or RDSP, right? And you have the gate here. This is the source, this is the drain. The current direction is going from drain to source as usual. Okay, what do you think should we do with the source? Or rather, if we want to, let me ask you this, if we want to only see, if looking upwards, right, looking upwards, if we want the resistance to be only RDSP, right, looking upwards, if we want to see a resistance of only RDSP, then what do you think should happen to this GM-VGS guy? The GM-VGS should be 0, right? So GM cannot be 0, GM of the PMOS transistor cannot be 0, but as a designer we can set the VGS to be 0, which means the gate has to be, the voltage difference between the gate and source has to be 0. Incremental voltage difference between the gate and the source has to be 0. So what is the easiest way to make the incremental voltage difference between the gate and the source to be 0? I will make the incremental gate to be 0 and I will make the incremental source to be also 0, right? So incremental gate to be 0 means what? So let's do the incremental gate 0. So we ground the incremental gate, the source is also incrementally grounded. If that is the case, then this guy goes off. If this guy goes off, what do you think will be the voltage at this node? What do you think will be the voltage at this node? The volt. So equivalent. If I simplify this circuit, so this, I should say this is gate of P, right? If I simplify this circuit, what do I get? I get Vi here, GMVi here, RDSN here, and on top what do I get? I get RDSP, to the other side is incrementally grounded. So what is V0? So clearly this RDSP and RDSN are coming in parallel, right? So your V0 will be minus GM times Vi RDSP parallel RDSN. Okay. So since we are looking into the drain of both the transistors, right, hence it is possible to get a large value of gain, right, as long as we keep the transistors in saturation. Okay, so this is as far as the incremental picture was concerned, but we also need to ensure that the incremental picture of the MOSFET is replaced by the actual picture of the MOSFET, right, actual symbol of the MOSFET including biases. So that's the next thing that we should concentrate. So let's do that. The n-Mos side, we know how to go about doing, how to go about biasing, so we wouldn't spend too much time using on that. But on top we need to put a p-Mos transistor. So here I have to put a p-Mos transistor, and we have to ensure that the p-Mos transistor is in saturation, right? Okay. So let's break the problem into multiple parts. Let's say that I have a p-Mos transistor. Okay. Let's say that I have a p-Mos transistor and I would want to bias it in saturation. Right. So what is the strategy? So what do we know? We need to ensure that VSG is greater than 0, or rather greater than some mod of VTP, right? VSG has to be greater than some mod of VTP. So which means what? We need to apply a battery between the gate and the source. So now we know that floating battery is impossible, but fixed battery is possible. So what should we do? So let's put a VDD here. And what do we need to do to the gate? We need to put some voltage. Let's say VDD equal to 5 volt, right? We need to put, and let's say we want let's say VSG is let's say mod of, let's say VTP equal to -1 volt, where mod of VTP is equal to 1 volt. So which means we need to apply a gate voltage which is lesser than 5 volts to make the transistor on. So let's choose a gate voltage of let VG be 3 volts, which means we need to put a battery of 2 volts between the drain and the gate of the device, right? So we know that this is again not possible, but we also know multiple ways of biasing, right? We can say that we'll put a resistor divider, right? So that the voltage difference between these two nodes is 2 volt, right? So let's say we did that. What should we do with the drain voltage then? What should we do with the drain voltage to ensure that this transistor M2 is in saturation? What is the constraint on M2? So this is VG. What is the constraint on M2? In case of an n-Mos, what was the constraint? For n-Mos transistor, for n-Mos, the constraint for saturation was VD had to be greater than equal to VG minus threshold voltage. For p-Mos, what is the constraint? Saturation, what is the constraint? It is, since everything is flipped, right? Everything is flipped. So this has to be VD is less than equal to VG plus mod VD, right? Okay. Why less than equal to? It's because the condition for n-Mos was the drain voltage how low we can get the drain voltage close to the gate voltage, right? We saw that if the gate voltage is, let's say, 2 volt, we can get the drain voltage 1 threshold voltage below the gate voltage, right? If we keep the drain voltage, if I lower the drain voltage below the gate voltage, below 1 threshold voltage, then I am having trouble. But note that PMOS is just the flipped. PMOS goes the other way, other direction, right? Since the PMOS goes the other direction, what is happening? All the conditions are also flipping. So in case of an n-Mos, there was a minima condition for the drain voltage. In case of an p-Mos, it will be a maxima condition for the drain voltage. So how high you can bring the drain voltage above the gate voltage, right? So hence, since this is a maxima condition, which means the constraint is the drain voltage has to be less than something. And as it turns out, in this case, using the same set of equations, we can show that the drain voltage cannot go higher than 1 threshold voltage above gate. Then you are in trouble, right? So the pictorial form of remembering this is if for an n-Mos, transistor. So let's say this is the gate voltage. Let's say this is gate. Let me color code. This is gate. This is drain. Source I am not sketching. So let's say this is the gate voltage that is fixed. and let's say threshold voltage is positive, which means that the drain voltage can go anywhere between higher than, can go as low as 1 threshold voltage below the gain voltage, right? So for saturation, if you go below this, this will be linear. For a p MOSFET, this is again gate, this is drain, right? And again, let's say our gate voltage is the same as in case of an n MOSFET, but the constraint here is the drain voltage can start from a lower voltage than gate and can go higher by 1 threshold voltage. Mod of threshold voltage. Note that threshold voltage of a PMOS is negative. This is the mod of threshold voltage. And if you go this side, this will be linear, right? So this, we are starting from a higher value and going down in case of a n-Mos, and we are starting from a lower value and going up in case of a p-Mos, right? So this is towards linear. This is towards okay, fine. So if that is the case, in this case, let's say this is 3 volt. Let's say we figured out that this is 3 volt. What is the maximum value of the drain voltage of M2 till which the transistor will be in saturation? The maximum voltage will be 3 volt plus 3 volt plus the mod of VTP, right? Since this is 3 volt plus the mod of VTP, right? So this will be, maximum is 4 volt. So all you have to do is to ensure that this voltage of M2 doesn't go above 4 volt, and then the transistor is in saturation, right? And what is the current direction? The current direction here is from source to drain, and if the transistor is biased in saturation, this is a voltage control current source. The current is some I0, some ISD, right? And if, how do you bias? And now we know multiple, we can simply put an RD here and stop, but now we know multiple ways of biasing our transistor, right, using constant current source, and that is something that we should explore as well, right? So let's explore that. So in case of an n-Mos, what was the most convenient way of biasing a transistor using constant current source? Obviously, in case of an n-Mos, the most convenient way of biasing was, one of the most convenient ways of biasing was through a diode connected transistor, right? This diode connected transistor creates a VGS, and we were VGS equivalent to the current source I0, and we then feed this VGS back to our one of the transistors of interest, and we bias a second transistor like this, right? So if we have to do the same thing for our PMOS transistor, what should we do? We note that we have this PMOS transistor here, right? We have the PMOS transistor. In case of the n-Mos transistors, in case of the circuit on the left, what were we doing? We were feeding a current into the drain of the device. In case of a PMOS transistor, we'll have to do the exact opposite. What is the opposite? Because everything is flipped, we'll have to take current out of the drain of our PMOS device, which means the constant current source will be connected at the drain, right? So let's say I0, In case of an NMOS transistor, what were we doing? We were connecting. How was the negative feedback across the transistor getting satisfied? We are connecting the drain and the gate. So we will do the same thing in case of a PMOS transistor. We will connect the drain and the gate, right? Okay. So when we do this, right? When we do this, what will be the gate voltage? The easiest thing to do is to say to find out the VSG. What will be the VSG? VSG will be, note that the current I naught in this case is half mu p Cox W over L VSG minus mod of VTP whole squared, which means that VSG is equal to mod of VTP plus under root of 2 I naught by mu p Cox W over L, where this is the overdrive of the transistor, right? Okay. So in this case, if this is the VTP, this is the VSG, what will be the gate voltage or the drain voltage in this case, because gate and drain are shorted? This will be VDD minus the VSG, right? And what will happen to this voltage if, let's say, threshold voltage changes? This voltage will adjust itself in order to give us constant current, because this has been biased with a constant current source, correct? Okay. So this is as far as the equivalence of this structure and this structure is concerned, correct? What about this structure? What should we do? This is VDD, let's say this is RL, and let me call this M1, right? So we need an equivalence of this, correct? So how do I get to the equivalence of this? So let's take this. Let's take a general case of a common source amplifier of an n-Mos, and we will try to reason our way out of what is the equivalent of common source amplifier in case of a PMOS transistor, right? So this is a, let's do the biasing first. Okay. So this is M1. So current is flowing from drain to source, right? Let's say I want to keep the same current in a PMOS transistor, and I want to make a PMOS common source amplifier using a PMOS transistor. Then what will you do? We know that these two are equivalent, right? We know that these two are equivalent. What is the equivalence? The equivalence is ID. In case of n-Mos, the equivalence is IDS is the current equation is IDS is half mu n Cox W over L VGS minus threshold voltage whole square. In case of a PMOS, it's ISD. The current flows from source to drain, half mu p Cox W over L VSG minus mod of VTHP, let me call it VTHP whole squared, correct? So if so what is the equivalence now? The current in the case of n-Mos flows from drain to source. In case of a PMOS, it flows from source to drain. So let's sketch the PMOS first. And we also know that the source is at a higher potential, and we also know that in order to ensure that this behaves like a common source amplifier, the drain has to be connected to the load resistance has to be connected to the drain, right? So load resistance connects to the drain, RL, and we know that the current flows from top to bottom. This has to be the ISD, right? And we also know that we need to hold, if we want equivalence of IDS and ISD, we need to have some held value between the VGS of M1 and the VGS of, let's say, M2, right? Right. So as long as I neglected the fact that I haven't really mentioned till now that mu n and mu p are not similar numbers. But if mu n were equal to mu p, and both of them have the same W by L, both M1 and M2 have the same W by L, then having the same VGS or VSG in both cases would have provided us the same drain current, right? So let's say I need some VSG. So what is the easiest way to get the VSG? So equivalent thing is to say I'll connect the VDD here, and we will apply the equivalent VSG here. And what should we do with that? What should we do with the RL, the other side of RL? The other side of RL should be incrementally grounded. In this case, there's no difference between an incremental ground and absolute ground. So this becomes a biasing of the equivalent biasing for a PMOS transistor. And now in case of an n-Mos transistor, if we want to turn this into a common source amplifier, what do we need to do? We need to put a voltage source in series with the battery. So in case of a PMOS transistor, we can also do the same thing. We can put a voltage source in series with the battery, and we take the output from the drain of the device, right? So what should we expect? What should we expect this incremental V0 to be? The incremental V0 should be minus GM times RL times Vi. What will be the quiescent V0? The quiescent V0 will be ISD times RL. So what will be total V0? Total V0 will be ISD times RL minus GMRL times Vi. Right? So why are we doing all these things? We are doing all these things because ultimately we have to go back to our requirement of how should we replace the load resistance and put a PMOS on top, correct? So let's which essentially means that we'll have to go back to our original circuit. Okay, so let's sketch the circuit here. So if we only concentrate on the biasing picture, and let's say M1 is in saturation, right? If M1 is in saturation, what is the we have some current I0 flowing through M1, and we want to replace the load resistance with a PMOS transistor on top, right? If we want to replace the load resistance with a PMOS transistor on top, and we also want the same current to flow through it, and you also want the drains to be connected to each other. So let's do the most obvious things first. Let's connect the drains together for the PMOS transistor. So if we want, let's say this has some VGS. So let's say this, we call it VGSN, right? And after doing some calculations, we figured that we want some VGSP on the PMOS transistor on M2. We want some VGSP for it to source a current of I0. Then we should put a battery of VSG P, which is equivalent to the voltage that is required to push in to source a current of I0. So now, what is the most convenient way of generating this VSG? We don't want to put a battery. We also don't want to put a resistor divider, because all the problems of resistor divider in case of an n-Mos will also come in case of a p-Mos. So what is the other way of biasing? What is the other way of generating the VSG? Other way of generating the VSG is this. right? Is this? So we'll basically steal this architecture, and what we will do is that we'll say that we have a constant current source I naught. I will diode connect it, right? And this voltage will naturally become VSGP, correct? The voltage difference between the VDD and the gate will naturally become VSGP. All we need to do is to apply this voltage difference, not the voltage itself, but the voltage difference. So that we can simply do by sharing both the source and the gate terminals of these two transistors. Let me call this M3, right? So essentially, what will happen if we bias our transistors like this? What will happen? What is going to happen? We'll see that as long as we are getting, as long as M2 and M1 are in saturation, as long as M2 and M1 are in saturation, that is a critical if, right? Right? So we'll see that the current through M2 and the current through M1 will be equal to I naught, right? But again, this is not the full story, because we cannot also bias M1 with a constant voltage source because of problems we have discussed before. So what is the other way of biasing this? We can say that let's take another current source and generate this voltage that is required to bias M1, right? The current mirror bias, you remember, right? So let me call this M4, okay. So and this current source becomes I naught, right? So the current mirror biasing between M1 and M4 is ensuring a current of I naught, and the current mirror biasing between M2 and M3 are also ensuring a current of I naught. So the current through M2 is also I naught, current through M1 is also I naught. These two are matched. As long as we can ensure that M1 and M2 are in saturation, then what? Then we know that the looking in impedance, the incremental looking in impedance into the drain of M2 is RDSP, and the incremental looking in impedance at the drain of M1 is RDSN. But now the question is, how do I apply an input? I mean, we know how to apply an input to the n-Mos side, and we'll essentially do that. So let's copy one of the, we'll basically use one of the earlier methods that we had, right? We apply an input, and what was that? If we have this guy, all we need to do is to AC couple our input here. This is some C infinity, and we put a resistor here, some RC, right? So this will give us the architecture for a common source amplifier, right, with a p-Mos load, right? So this is a common source amplifier with a p-Mos load, right? I should say p-Mos current mirror load. This is also called this load is not a physical resistor. This load is the load, the incremental loading that M2 is providing is through a p-Mos. It's an active device, right? Because it requires a VDD to get biased properly. So this is also often called active load, right? Or active load. Okay. So what I would request you now is to sketch the incremental equivalent of this entire model, right? Do it yourself. So basically all you have to do is to replace each of these transistors, all the 4 transistors, with their incremental equivalent, right? Assuming M1 and M2 are in saturation, right? That is not guaranteed. Assuming M1 and M2 are in saturation, we put the sketch the incremental equivalent of this, and we find out the gain. Where will you take the output? Clearly, we will be taking the output at this node, because this is the drain terminal of M1 and M2, right? Yeah. So please do it, and I'll see you in the next class.